So the last thing we're going to talk about in this section is a result known as the law of large numbers. So the law of large numbers is an extremely important result for like the intellectual underpinning of this course. It tells us a lot kind of about why probability is so useful for analysing data. It'll tell us a lot about why things like the expectation, which we just like put down as some definition, is so important. It will tell us about connections between the mean of data and the expectation of a random variable. So it's like intellectually, it's one of the high points of this course. On the other hand, it's not like a result that you'll be using lots. Like, the formula for expectation is something you use all the time. It's not very often you actually use the law of large numbers, but it's like really important to understand why probability is like such an important topic. And when this result was first proven, back in whenever it was proven, it was like considered to be the pinnacle of mathematical probability. So the law of large numbers is about taking lots of repeated experiments as a random variable. So you'll remember that we said that repeated experiments are modelled by independent and identically distributed random variables, IID, independent and identically distributed, which means that they all have the same distribution, but they're independent. And so, that's modelling the idea that we repeat an experiment over and over again. So let's just set that up for a start. So here we're going to have x1, x2, xn being IID, independent and identically distributed. And so they're all going to have the same mean, which I'll call mu, the same expectation, which I'll call mu, and they're all going to have the same variance, which I'll call sigma squared. Okay, so when we had data, just some numbers, we allowed ourselves to add up those numbers and divide it through by n, and that gave us something we called the sample mean. So now we've got a bunch of random variables. Well, we could add up all those random variables and divide by n, right? That's certainly a thing we could do, right? Nobody to stop us adding up all these random variables and dividing them by n. And we could call that a mean as well. X bar. I'm putting an n on my x bar to remind myself that this is the mean of n random variables. Note, because all the x's, x1, x2 up to xn, are random variables, this x bar is a random variable as well. Right. We've just defined a random variable as being a function of other random variables. Add them all up and divide them by n. So for this new random variable, xn, this mean, we could say, well, it's a random variable, so what's its expectation? What's its variance? Those are totally legitimate questions for us to ask about any random variable, so they certainly are for this one. So we could say, what's the expectation of this mean random variable? Well, that's the expectation of 1 over n, x1 plus x2 plus dot 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 plus xn. Here we can use all the results we've seen on linearity of expectation, right? Which is that we can take the 1 over n outside, and we can do all the expectations separately. That's linearity of expectation. We know that all these expectations are mu. It says so at the top of the screen. That's 1 over n mu plus mu. So we've got n mu's we're adding up, then we're dividing through by n, so that all comes out as mu. So the expectation of this new random variable, the mean random variable, is equal to mu. We could also look at the variance of this x bar. So again, let's remind ourselves that this is the variance of x1 plus x2 plus dot 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 xn. Now the first thing we can do is we can take the 1 over n outside the bracket, but we have to square it, don't we? When we've got a constant inside a variance, we have to remember to square it. That gives us a 1 over n squared. Now, all these random variables are independent. We said they're IID. So when random variables are independent, we can make the variance of a sum of a variance, right? So because they're independent, and only because they're independent, we can then write variance of x1 plus variance of x2 plus variance of xn. Those are all sigma squared, and there's n of them. So one of those n's cancels with one of those n's, and we get sigma squared over n. So in conclusion, when we take this mean random variable x bar, it has mean mu, and it has variance sigma squared over n. So let's think about what happens when n gets big. So when we're repeating this experiment a very large number of times. Well, the expectation is staying the same, right? The expectation is just remaining at mu. But this variance, as n gets bigger, the n on the bottom is getting bigger and bigger. So that's making this smaller. Right, so this is staying constant as n gets bigger. This is tending down towards 0. So if you think what this looks like as a random variable, you've got a random variable with mean mu, so mu's kind of in the middle, and the variance is getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. So like the whole random variable is like collapsing in on the expectation mu. And so that's what the law of large numbers says. The law of large numbers says if you take this mean random variable x bar, it eventually collapses down to mu. So let's state that as a theorem. And this is the law of large numbers. You might also see this in books referred to as the weak law of large numbers, because there's a very similar result called the strong law of large numbers. So let x1, x2, xn, the IID, independent and identically distributed with expectation mu, and let x bar n be this mean random variable. Then, as we said, this is just going to collapse in on mu as n tends to infinity. Now, this is all you actually need to know, but for the purposes of like honesty and detail, I'm just going to add a little bit more here. You don't need to pay attention to this if you don't want to. But some mathematicians are very picky about convergence, and so they would want me to note that this is a particular type of convergence known as convergence in probability, and they would perhaps want me to specify that this means that for all epsilon greater than 0, and I apologize if it is now sounding like an analysis course, the probability that x bar, this mu minus mu, greater than epsilon, to 0. So you don't have to worry about the last bit if you don't want to. It's just kind of saying that the probability that the mean is far away from this expectation mu tends to 0. But again, what we're interested in is in this general principle. And what the general principle says is that if you add up lots of random variables and divide through by n to take a mean, then the mean of those random variables homes in on the expectation. So if you think about, say, taking Bernoulli P random variables, this says that the number of successes, or the proportion of successes, hones in on the probability. So if you do lots of experiments that are Bernoulli P, succeed with probability P, and then you see what proportion have succeeded, homes in on P. Now, I don't know if you remember this, but right at the beginning of this probability section of the course, in section 2, we talked about frequentist probability. Frequentists say that, like, the definition of probability is the long-run proportion of times that something happens. So, if in the long run it rains on 40% of days, then the probability it rains is 0.4. But that's what this result, the law of large numbers, has said, right? In the special case of a Bernoulli random variable, it tells us that if we take lots of repeated experiments, then the proportion of successes does indeed home in on the probability. This also allows us to say other things like, when we take means of random variables, that homes in on the expectation. When we take sample variances of random variables, that homes in on the true variance. So again, it's not like you need to use the law of large numbers. It's really telling us why so much of the ideas we have in probability and statistics work. Because when we do repeated experiments, we end up getting the correct answers on average.